Well, it's with great pleasure that I introduce John Greedan, the 2024 Bertram, Eugene Warren Diffraction Physics awardee. The Warren Award is given for research into the physics of solids or liquids inspected by X-ray, neutron, or electron diffraction techniques. John's research focuses on the structure-activity relationship of transition metal oxides and perovskites. These materials must be inspected by a variety of techniques to understand their activities. John has utilised X-ray diffraction and neutron diffraction techniques to interrogate his materials. Today, he will present his findings of these materials and exploring the proper structure, property, Nexus, and perovskite, pyrochlore oxides. But before that, I'd like to present John with the award.
Thank you very much. I'm quite honored to receive the Bertram Warren Award. I want to, as people often say, you're at the same time thrilled and honored and humbled. I don't know how you pull that off, but that's what I'm feeling now. I want to thank the people who are responsible for this award. This would be the folks who nominated me and the folks who wrote letters of support. And then the ACA Award Selection Committee, who evidently believed much of what was in the election. I never had the opportunity to meet Professor Warren, although it wouldn't have been absolutely impossible. It never actually happened. My closest association was with a colleague of mine from McMaster. When I joined in 74, this colleague actually had obtained his PhD in physics at MIT, and he took Professor Warren's famous course in X-ray diffraction, and he claims to have received a passing mark, which if you've ever actually read Professor Warren's monograph on X-ray diffraction, you'd be impressed by the achievement, I think. Okay, so let me, I guess everyone can hear me okay, so let me get started. So I'm going to start with perovskites and then say a few words later on about pyrochlore oxides. Okay, so this is a slide I borrowed from Paul Atfield. So you might have seen this before. The perovskite is a natural product, which when I say that, annoys my organic chemistry colleagues. And it's named for this very dapper-looking academician. Of course, there's perovskite itself. If you type perovskite into some database, you will come up with some astonishing number of hits. And of course, even in this conference, I've attended essentially all the sessions I've attended. There's been at least one perovskite paper. It's a very popular sort of thing. I'll just quickly review. I don't think the perovskite structure is a revelation to anybody here. So let me just whip through some things. Of course, the ideal form crystallizes in this primitive PM bar 3N structure. There are the formula is ABX3. There's two sites, a large cation site and a small cation site. The small cation is invariably octavely coordinated. The large cation in the cubic phase is 12-4 coordinated, or it can be smaller. And for about 100 years, we've been using Goldschmidt's tolerance factor to predict the stability of perovskite structures. Of course, you're not stuck with the PM bar 3M symmetry. You can achieve all these other symmetries by clever rotations of the octahedra. These are generally motivated by an effort to accommodate A-side ions, which are not quite big enough to like 12-4 coordination. And we saw a lot of Brandon's talk a couple of days ago showed some very interesting video of how these twists and things can happen. Our approach has been slightly different. We take the perovskite structure as a template and try to make new materials with perovskite structures associated. I'm not going to go through, we've done all of these things. I'm not going to go through all of them, of course. We're going to focus mainly on two, but you can do all kinds of things. You can put different ions on the B site. If you choose them correctly, you will get something called a B site order double perovskite. And to my astonishment, there's 1,200 of these things now, according to the recent review article. You can do substitutions on the A site. You can create vacancies on the A site. But the two things, two things we're going to talk about are the intergrowth possibilities. The most famous one is with the sodium chloride to produce the Robertson Popper phases. And we're going to take oxygen out, and we're going to end up with brown millurite and brown millurite related phases. Those are the two we're going to spend most of the time on. Okay, so another thing I'll mention is that perovskites are very friendly to chemical substitution. If you ignore the rare gases and all the elements that glow in the dark, you can accommodate about more than 90% of the chemical elements that are easy to use in the perovskite structures. That accounts for the popularity in part and also the amazing number of phases that come to existence. So I'm going to talk first about the Robertson Popper phases, and then something about the oxygen deficient phases of the brown millurites, and then finish with something about the pyrochlores. Okay, so the Robertson Popper phases here are part of the gang that involved with that work. Larry Greedan, Ross Stewart and his stand club, Andrew Grubner, Marilla Dragomir, a postdoc in our group, and Paul Dubé, a member of the Barkhouse Institute of Material Research staff. Okay, so the so-called N=1 Robertson Popper phase has been well studied. It crystallizes in the I4-MMM space group. You have the perovskite corner share perovskite layers displaced by 1/2 vector. And the large cations can be all sorts of things, strontium, barium, and lanthanum. Now, the source of interest in these materials, which are in the structure type, which is also sometimes called the Phys nickel chloride structure, is the opportunity for low-dimensional magnetism, in this case, two-dimensional planar magnetism. As this little cartoon shows, if you have intraplanar antiferromagnetic nearest neighbor coupling, and you can see the configuration here, the layer in the middle of these two, the spins are actually frustrated, so you have 4 spins up and 4 spins down. A lot of these, as I mentioned, have been studied in the past. Some of you might recognize that thing as cuprate as the precursor of the cuprate superconductors a few decades ago. But no one had really looked much at the case when manganese is the small cation. So that's what we set out to do. Okay, so this is part of Mario's PhD work, and this is some of the last neutron diffraction data that we took at the McMaster reactor. And we started looking at this strontium lanthanum manganese Robertson Popper phase, and as it turns out, it's an antiferromagnet with a Néel temperature of 128 Kelvin. This is a magnetic structure, as you can work out. Other people have grown single crystals and worked out even the spin wave structures. This is a well-studied and well-known material. Okay, so now we wanted to study the magnetism of this and related materials, where we substitute some of the strontium with barium, and we went to a polarized neutron source at TILL. This is D7. In this instrument, you can separately measure the nuclear magnetic and spin incoherent contributions to the magnetic cross-section. So here are some examples. This is a strontium, all strontium case. And you can see that when you get above the nail temperature, 128, you start seeing these very funny line shapes. And the line shape, these funny line shapes persist all the way to the all barium case, where we substituted all of the strontium with barium. And we don't see anything at all. The magnetic cross-section is in fact relatively featureless. It's practically paramagnetic in this sense. So, right. Now, whoops. Eek. Oh, damn. Oh, here, sorry, okay. So, right, okay. So, as you might have noticed, some of the line shapes, which we got above the nail temperature, were very odd. And in fact, they, of course, have the Warren line shape. And this is Warren's famous paper, May 1st, 1941. This is 7 months before Pearl Harbor, for those of you just for Phys for reference. And it's actually a year and a month before I was born, believe it or not. So this is a venerable paper. It's been cited about 1,800 times if you look it up in the database. And it's a single author paper. How many single author papers have you seen in your lifetime? Not very many. It's about 6 or 7 pages, and it contains at least 1 or 2 quadruple integrals, which I had never actually seen before. And anyway, at the end of the quadruple integrals and all the other stuff, you end up with this formula for the diffraction power for this funny material. This is actually a diffraction pattern of carbon black, which is a material which has graphite type layers which are randomly stacked in 3 dimensions, so they're actually strictly 2-dimensional material. And so Professor Warren was able to show that this weird sawtooth line shape is derived from this type of a stacking sequence where you have really just scattering from a two-dimensional system. He was studying carbon black, and I guess we can forgive him for not having discovered buckyballs, right? Because there's a teeny tiny fraction of buckyballs hanging out in carbon black. I think maybe we're going to pass on that one, all right? So anyway, this is the formula. Not absolutely obvious. It gives us, looking at it, it gives us this line shape. And you can get the correlation and all those sorts of stuff. Okay, so now the Warren formula was the go-to method for analyzing 2-dimensional scattering for over 70 years. And in about 2013, 2014, some other methods that were introduced. You heard about the one from Princeton in the Etter talk, and at roughly the same time, Joe Pattison and Andrew Goodwin and Ross Stewart came up with another approach called spinbird. Okay, so here this is a reverse Monte Carlo technique, which is very popular these days. And here are some fits that we've done to the data. Here we have this strontium lanthanum manganese compound, the all-strontium phase, above the nail temperature, and you can see perfect Warren line shape. But this is not using Warren's formula; it's using the reverse Monte Carlo method, and so it's model independent. And among the ways that you can display the data, here's one. You have the spin correlation function as a function of distance in real space. And these dots represent, the symbols represent real space translation vectors from the origin to the spin. And you can see the intraplanar guys have a strong correlation. And the spins at exactly the 1/2, 1/2, 1/2 layer have no spin correlation. This is a perfect realization of the two-dimensional frustration. In the case of the barium phase, all barium, remember we saw this relatively featureless thing, and when you apply spin burst to this, you get absolutely no spin correlations. Okay, so, well, we thought we would, why not? Let's grow a single crystal. You can always learn stuff from single crystals. And I want to acknowledge the contributions of Hannah and Anthony Dokowski to the McMaster Crystal Growth Lab. They trained scores of students, undergrads, graduate students, postdocs, visiting scientists, faculty members sometimes, and they were instrumental in organizing several successful crystal growth summer schools. So this is Marilla Gargomer's work, and so we use the optical flow zone method, and there's a crystal that resulted, and we get all sorts of beautiful looking alloy patterns. The only problem is that the grown crystal composition of the crystal isn't actually what we wanted. Right? This happens in crystal growth. This is not Hannah's fault. We're not blaming her. This is the kind of stuff that happens in crystal growth. Right? What you put in is not always what you get out. And so, in the spirit of lemonades versus lemons, lemonade versus lemons, this is what we got. Let's go ahead and measure the damn thing. So. Here are the measurements that Morella and Paul Dubé did. We found something quite remarkable. If we measure its susceptibility with the field applied along the z-axis, we get what is basically classic spin glass behavior. I'll show you some other evidence for that. So this is perfect spin glass behavior. When we apply the field normal to the z-axis, we get no spin freezing whatever, down to a base temperature of 2 Kelvin. The other two slides are just efforts to show what we should see in a polycrystalline sample, because we're clearly not going to grow crystals of all the compositions. We tried once and it didn't work out that well. Now I just want to say, what's happening here when the field is perpendicular to the z-axis? There's no evidence of freezing, but it's also not really paramagnetic. If you look very close to the base temperature, you see that the curve is not actually, it's supposed to be a hyperbola, it's supposed to shoot up, and it doesn't. There's some effort, there's some evidence that it might be turning over a bit. So this might be evidence of spin correlations now forming in the similar directions. We have, for the purists, we have other evidence of the spin glass character, AC susceptibility, frequency, fitting the Meidoff criterion, linear heat capacity at low temperatures, and all sorts of things. So it's clearly a spin glass, but only in that one direction. So the ground state of this material, I like to characterize it as kind of a spin glass gyroscope. I don't know how many people have seen a gyroscope. It used to be a children's toy before electronic handheld devices took over, and there's no more children playing with gyroscopes anymore. It's not unheard. And it's the only one other, it's almost unique, the only one other well-documented example of a anisotropic spin glass, and this is iron titanium material. Okay, so we're left with the problem of what on earth is the oxidation state of manganese? For example, is it, again, we have this not 1-to-1 barium to lanthanum ratio, and so does it contain some manganese 2+ with 4 oxygens, or in fact, is it slightly oxidized, which would retain the old manganese 3+ oxidation state? Okay, so here we have to use other techniques. We have a collaborator, and we took some L-edge Zane spectra, manganese L-edge Zane spectra, and this is our samples here in sort of red. This is what you would get if you had any manganese 2 plus. So there's no evidence for manganese 2 plus. We have to have the all manganese 3 plus, which leaves us with the problem where's the bloody oxygen? Okay. Okay, there we go. So as it turns out, completely by accident, we had some pretty good neutron diffraction data. We all attended a summer school at Oak Ridge, and part of the deal was you could run a sample on Nomad if you want. So she took the stuff. So before we realized it was a problem, and she obtained Nomad data. Nomad is, in addition to being a PDF instrument, it's also a decent powdered photometer. And the great thing, of course, is that you can collect data out to very high Q, which is very useful in refined occupations. And so there was some suggestion from earlier work as to where the interstitial oxygen might go. It goes into that site. And so she tried that model and refined it just fine. So we have a slightly oxygen excess Rosen copper phase. Okay, so what is the story with barium, lanthanum, and manganese oxide? We couldn't get a single crystal, but we could get, of course, we could get powders. And when we obtained the powder data, it looks exactly like we expect for a powder sample of the anisotropic stimulus. So finally we understand that the all barium phase is an anisotropic stimulus. And how can we justify this? Here's an attempt. There are, with manganese 3 plus, you of course have it's a gonteller ion and you have a distorted octahedron. And so the splitting pattern of the EG orbitals looks like this. That's where L is below dx squared minus y squared. And there's a antiferromagnetic pathway. And there's also a ferromagnetic pathway where the spin is transferred to the empty dx squared minus y squared orbital. However, this pathway is less favorable in general because there's an energy splitting between the two due to the Antello distortion. So in strontium, all strontium phase, the antiferromagnetic interaction wins out. But in the all barium phase, there's a chance that the ferromagnetic interaction will be competitive. And just to remind you what happens here, you can estimate the critical temperature for a two-dimensional system. And there are two components. One is the one you might expect, which is the exchange interaction between the layers. There's also the 2D spin correlations. And so if you can kill off the 2D spin correlations, you will essentially kill off the magnetism. And this is supported, this is not just a bunch of diagrams that I produced, this is supported by some DFT work. Okay, so if we look at the octahedron, the manganese oxygen octahedron in the two materials, the thing that I'm going to point out is that you can define a distortion index here, and you can see that as you go from strontium to all strontium phase to all barium phase, the distortion index is significantly decreased. And a result of that is that the antiferromagnetic interaction will decrease and the ferromagnetic interaction will increase. And so it's possible that in this case, you have essentially compensating antiferromagnetic and ferromagnetic interactions. And this would kill off the in-plane correlations and you would get to a spin glass state. There's some evidence for this. If you measure the Curie-Weiss state of the intercept of the susceptibility, inverse susceptibility curve, in principle, this is a sort of an algebraic combination, sum of all the exchange interactions, and you have an antiferromagnetic and a ferromagnetic exchange interaction. If the all strontium case is strongly antiferromagnetic, as you go to the barium case, the theta value begins to approach zero. And so we're talking about that as it. Okay. as proof for our hypothesis. Okay, okay, let's move to the second topic. This is now having to do with oxygen vacancy ordering in the perovskite. And I take this opportunity to introduce all the folks who supported our work over the years. Some of them don't exist anymore. The neutron source at Los Alamos doesn't exist anymore. The neutron source at Chalk River doesn't exist anymore. And this is, in part, this is Farshid's work. Okay, so basically what we're going to be talking about in this section is nothing. Right? We're talking about vacancies. There should be something there, but there isn't. So we're talking about nothing. And you might be surprised to know that nothing is kind of a major cultural theme, at least in Western civilization. Here's an example. You have, of course, the famous comedy from Shakespeare, and you have what is not a comedy from Jean-Paul Sartre, and then eventually this, for some reason, has led us to George Costanza. So I'm responsible for that. Okay, so as I mentioned, this is primarily the PhD thesis of Farshid Zanipur, who's now at the University of Louisville. This is a New Yorker cartoon. You have to look carefully at the animals that are being herded there. So we're talking about, we're talking about the herding of oxygen vacancies. Okay, so we're going to look at some specific perovskites to start with, oxygen deficient perovskites. These are going to be based on iron and, for the most part, manganese. So we're going to, you can formulate them this way with 6 minus delta or 5 plus y. We'll choose the second representation, and we're going to focus on the y equals 0 cases where we have substituted about created about 16% of vacancies on the oxygen site. Okay, well, when the A site is all calcium and the B site, half the B site is manganese, in any of these ratios, we get full oxygen vacancy ordering. And this leads us to something called the Brown-Millerite structure, which is shown on the left. The main consequence of in contrast to a random vacancy disordered perovskite on the right, and the consequence of the vacancy ordering is that you get alternating layers of octahedrally coordinated B-side ions and tetrahedrally coordinated B-side ions. And this very large superlattice, if you like, which is 8 times the volume of the primitive perovskite itself. Okay. The perovskite layers, the octahedral layers, are just like perovskite, they're corner-shared octahedra. The tetrahedral layers are also corner-shared, but of course, they're sharing only one corner. And it's the tetrahedral layers that defines the overall symmetry for Brown-Millerites. I'm not going to go into too much detail, but as it turns out, you can have both right-handed and left-handed chains. The orientation of the chains, both within the chains, within the layers themselves and between the layers, determines the symmetry. And I'm not going to go into detail here, but you get a whole range of mainly orthonomic space groups, depending on the relationship between the intralayer correlations between the chains and the interlayer correlations. Now, the interesting thing is that the space group actually tells you right away how disordered or ordered the chains are. For example, in this case, BDCM, we have strong intra and interlayer chain ordering. In PNA and B2M, we have interlayer ordering only. In IMMA, the interlayer ordering is completely destroyed, but the chains still exist. They're just randomly distributed. There's no right-handed, left-handed correlations. And then finally, of course, we can go all the way back to PM or 3M, where there are no more chains. Everything is completely destroyed. And so the space group symmetry is diagnostic of the, basically like the oxygen vacancy disorder. Okay, so we're going to look at then the all calcium, iron, manganese phase, and some other, and two other cases where we substitute 4 calcium, 1 strontium, and then 2 strontiums to see what happens to the structure and properties. Okay. Now, let's start with this phase, equal amounts of manganese and iron. And of course, we get asked the question, are we going to get D-site ordering? If we work out the optimal site preference energies for manganese 3+ and iron 3+, it strongly suggests that we'll get strong B-site ordering with manganese in the optimal site. But how are we going to know this? If you notice, iron and manganese are adjacent elements in the periodic table, right? And so how do we do that? Well, I'm going to propose one method, which is neutron diffraction. This is one of my favorite little superheroes, Captain Neutron. He's not as apparently fit as some other superheroes out of 6 packs there, but he's an elementary particle. So we should give the guy a break. And but the important thing I'm going to point out here, and before you're composing your hate emails, I know you can do this X-rays, synchrotron X-rays with tuning, wavelength tuning, but I think it's really much simpler to do this with neutrons. Because if you look at the pattern of scattering lengths across the series, you can distinguish every adjacent pair of transitional ions, transitional atoms, very, very easily with neutron diffraction. And the very best case, as a matter of fact, is iron manganese, because manganese is a very large negative scattering length. Iron is a very large positive scattering length. So that's what we do. And sure enough, these were data taken at the now extinct Canadian neutron beam source, Chalk River. And sure enough, the site ordering is way over 90% for manganese on the optimal site, on the optimal site. Okay. Okay. So we get the strong site preference energy that we expect, the strong optimal site occupation for manganese. Now we're going to compare what we get when we substitute 1 strontium for calcium and 2 strontiums for calcium. Okay. Well, 1 strontium for calcium. Well, we get a change in space group symmetry. We're now ion than A. And if you look at the 2 patterns, you can probably see that the peak width is now significantly greater for the 1 strontium case than for the 1 calcium case. This, of course, is a measure of the order length, the length scale of ordering of the oxygen vacancies. And sure enough, we can, by fitting, say, that peak to Lorentzian, it actually fits pretty well to Lorentzian, we can estimate a domain size of about 20 nanometers. So we're doing nanochemistry without any effort at all, no fooling around, just changing the calorie. Okay, and then finally, if we substitute all strontium on that site, we destroy all the chains, we completely destroy it. We're back to PM bar 3. Okay, so so we can ask the question in the simple cubic, the primitive cubic phase, what happens to our chains? Do they exist at all? And of course, the way to get at this problem is using total scattering. It used to be known as the neutron pair distribution function analysis. And there was, of course, a session this morning on total scattering, and everybody, I don't know how many people attended, so I'm not going to dwell on some of these details, but you basically measure a diffraction pattern out to insanely large millennium transfers, you truncate somewhere, and Fourier transform to get the G of R. And you can use the same data, of course, truncating at a lower Q to carry out structural analysis. Okay, so this is basically the sort of thing you get, the diffraction pattern, and then the G of R. Each peak in the G of R, the intensity of each peak is proportional to the product of the scattering lengths of the two elements involved in the pair and the number of pairs that you've got at that distance. Okay, just to, once again, just to show how this works, what we mean by total scattering, you get information both on the average structure of these very short drag peaks, and then a huge amount of information in the background. Okay, so as we heard this morning, there are at least two ways to analyze the G of R, the small box and the RMC large box approach. The small box approach seems to be falling out of favor, but we did this work quite a while ago, and so we use both approaches. If you try to model the data using the cubic model, of course you've got a remarkably lousy fit, as you would expect. However, again, within the spirit of the small box approach, if you now go to something like a Brown-Millerite model, of course you get a better fit, and of course that's not a big surprise. You have many more adjustable parameters to play with. Now, when we were doing this work, the RMC techniques were just sort of emerging, and so we were working with Graham King, who was as far as I know, was the last instrument responsible at the Lewin Center for the PDF instrument. He now works, interestingly enough, at the Canadian Light Source. And so we carried out RMC modeling, and of course you do a whole lot better, as you might know, with RMC. That is, if you compare that thing with that one, it's a much better fit. And if we look at the near neighbor, the very close neighbor bonding portion, you see quite a nice fit with the RMC approach, and a much poorer one with the small box. So let's just briefly examine what's going on with the small box approach. Is there any sense at all in talking about a local Brown-Millerite structure? Is there any part of the local structure that looks even remotely like a Brown-Millerite? And so we can examine that again with the PDF results. There's two main differences between the randomly ordered randomly ordered perovskite, distorted perovskite, and the Brown-Millerite. Of course, there are specific sites for iron and manganese ions, and they are separated into layers. The specific sites are octahedral for manganese, tetrahedral for iron. I won't go into a lot of detail on this slide, but you can work out where you should see peaks in the G of R just by looking, not by doing anything fancy, just by looking at the damn thing. And so the end result of this analysis is that in the G of R, in the actual G of R itself, you should see a strong peak at about 3.4 angstroms and practically nothing at 3.89. Okay, what do we actually see? Is I'd like to paraphrase one of the 20th century's more interesting thinkers, Lawrence P. Barrow. Here's 3.4 angstroms. There's nothing there in the G of R. And there's something at 3.8, so it's completely, you get the result is completely opposite to what you would predict if you had anything resembling a Brown-Millerite. Okay, let's look at the local environment peak. One of the nice things about the RMC large box approach is that you can extract local or partial contributions, and so you can actually, in fact, you can extract the nearest neighbor bonding regime for manganese oxygen and iron oxygen. And if remember, in the Brown-Millerite, this is an octahedral site, a tetrahedrally distorted octahedral site. So you should expect to see maybe two peaks in a ratio of about 2 to 1. Right? There's two axial and 4 plane. In fact, what you get is something like 4 to 1, and that is consistent with square planar coordination, not octahedral coordination. And interestingly, of course, manganese 3+, there's another phase which is not a brown mineralite, strontium 2 and 5. And in this phase, manganese does in fact have a 5-fold coordination. The iron case is also interesting. It should be tetrahedral, 4-fold coordination. This is the partial. You get this rather large blob, which could be consistent with any coordination number from 4 to 6. And so that's certainly not brown mineralite like, and we went actually to our colleague Dominic Ryan. That's Dominic's. He actually owns a plane. That's a Dominic in his plane. And sure enough, you can analyze the muscars, 59 muscar spectrum in terms of 3 sites. So it's a very complicated environment for iron. So then the local structure is down below. Okay. Now, so what about the effect on properties? See, iron, when we have all calcium, we get perfectly well-defined magnetic ordering. In this case, with this particular composition at 465 Kelvin, and we can get the so-called G-type magnetic structure, which all the spins are, neighboring spins are anti-parallel. These are the magnetic reflections that are more intense than the nuclear reflections, so it makes it quite nice. Now what happens with the strontium phase? Well, here's a similar susceptibility curve for this SR2, Fe, and then 5. And you see all of the any indication of long-range order seems to be gone. And we get this zero field cool divergence somewhere below 50 Kelvin. So this, if you remember what we saw earlier, this looks vaguely like maybe a glassy transition to a spin glass state. But in fact, it's not. When we look at the neutron diffraction, we actually see 2 magnetic peaks. This is the red curve, the red data are at 290, the blue at 4 Kelvin. So we see 2 drag peaks that index just perfectly on the cubic cell. The ending, however, as you can see right away, I think they're much broader than the nuclear peaks, so they're not resolution limited. And so we're looking at some kind of antiferromagnetic domain with a dimension of about 50 angstroms. And we're calling this something like a superparamagnet. Superparamagnet is a cluster of a large number of spins. If they're antiferromagnetically, normally these are ferromagnetically coupled, but if they're antiferromagnetically coupled, you could still get the surface spins. There would be some fraction of the surface spins which will not be coupled to the bulk particle until you can get the superparamagnetic type behavior. Okay, so when you get to be my age, you start looking for hobbies, and one of the hobbies that my wife and I share, she's sitting here, is bird watching. And so we've been doing it actually for 40 years, but lately we're doing more of this, just to say that. And you can criticize bird watchers. They spend hours, days, weeks even, walking through forests, wetlands, and even more inhospitable environments. In the off chance that they might, for 2 or 3 seconds, get a glimpse of a rare warbler or a tanager or a bunting or something like that. And those criticisms are all perfectly valid, I have to admit. However, when you're out in nature like that, you learn a lot of life lessons. For example, here's a pair of wood ducks. This is the Drake wood duck is North America's gaudiest duck. The plumage is the most striking. And the hand's not bad either. She has this cute little eye patch. And here's a bucolic scene. They're sitting on a log, just hanging out, having a great time. But there are, of course, consequences to this sort of thing. And what's that? And here's the consequence. See, maybe no sign of the Drake anywhere, right? No, actually, there's actually 12 ducklings. I couldn't fit all 12 into my screen. So bird watching, not total way off. Okay, so I'm going to finish by saying something about the pyrochlore oxides, which we spent quite a lot of time. Pyrochlore, again, a natural product. Pyrochlore crystal. In nature, it's this niobium oxide with hydroxides and fluorides and sodium and calcium. The synthetic pyrochlores are, in fact, in general, slightly more, precise in composition. There's A cation and B cation and 7 oxygens. In fact, the oxygen sites can be divided into 2 sites, oxygen and oxygen prime. It's always described in FD bar 3 on space group. Here are the atomic positions. There are, I just want to acknowledge many other people who worked on pyrochlores from a long time ago. Some old friends, Master Bertram, from DuPont and Oregon State, or Slate, DuPont and Oregon State. Brendan Kennedy, some of you probably know, from the University of Sydney, was a big pyrochlore advocate. And we had two of my PhD students did their entire PhD thesis on pyrochlores in 1982 and 1991, long before pyrochlores became quite so popular as they are now. And you don't learn a lot by looking at a unit cell representation of the pyrochlore structure. There's 88 atoms in the unit cell, so we'll split things up a bit. There's some similarities with perovskite. The small cation site is octahedrally coordinated, and the octahedra share corners. But they're very constrained. There's not a whole lot of opportunity for tilting, and so there's not a nice family, space group family tree of things you can get to by tilting octahedra. You don't tilt. And the angle, the EOB angle is pretty well rigidly held at about 130 compared to perovskites, in which you have, of course, a wide range of angles. The B site oxygen atoms are all equivalent, and the octahedron is a rather squashed thing, and the angles, the oxygen, B-side oxygen angles range from 90 or 80 to 99 degrees. The most remarkable thing, however, I think about pyrochlores is the A site. The A site environment is apo coordinated, and there are two particularly different distances. There are 6 sort of axial atoms. If there's any chemists in the audience, there may not be. This looks exactly like the chair form of cyclohexane. Okay? It's that sort of configuration. But you have these 2 axial oxygens, which are very, very short distances with respect to the A side line. And this introduces a very, very strong axial distortion to that site. And that we'll see is very important. The most useful thing about pyrochlores, both the 16D and 16C sites are occupied, so they share something with spinels in which only one of those sites is occupied. And as it turns out, for both sites, if you look only at the metal site positions, they form perfect 3-dimensional arrays of corner-shared tetrahedron. And of course, this is the ideal environment for geometric magnetic frustration. Here's a triangle, and here things get even worse with the octahedron. It's impossible to satisfy all of the anti-ferromagnetic constraints on the corners of an octahedron. So, as it turns out, you can use this sort of stoichiometric situation to subvert the third law of thermodynamics, right? Now, here's a structure field map of pyrochlore oxides. You can see mainly looking at the A-side ions are mainly lanthanides. B-side ions can be any of these species here. Some of them are stable only under high pressure conditions, and there are many others that are not included in this figure, which have been realized lately using high pressure techniques. But this is the sort of equivalent, if you like, to the Goldschmidt tolerance factor for perovskites. So completely, just in the spirit of studying the structure property relationships across the series, where we replace the A-side ion, we make the A-side ion a rare earth, and just cruise across the rare earth series to see what happens. This was in 1986. We made a remarkable discovery. I've included, by the way, that not everybody in the audience may memorize that part of the periodic table. So here's the dividing line between gadolinium and terbium, their adjacent elements, and neodymium, samarium, and linium are metals. These are resistivity curves. When you get to terbium, they're insulators. I've included yttrium, not in its expected place in the periodic table, but where it should be with respect to ionic radius. And so there's a clear metal insulator boundary between gadolinium and terbium, which is a remarkable thing. And this work was done primarily by Neo Sato of Niigata University, and he was visiting as a postdoc. Okay, just a couple of comments on the metals. There are ferromagnetic metals here with the magnetization curves. You've got almost perfect saturation. They're unusual, they're remarkable because they're ferromagnetic metals, which is quite rare for 4D compounds. Previous to this, the only other example was strontium glutamate. The neodymium compound has attracted a lot of attention because of something called an anomalous Hall effect. I don't know how many people knew that you had an anomalous Hall effect to begin with, but that you can have an anomalous Hall effect, and you can ask me about this later if you like, but it's quite attracted a lot of attention. But the main thing of interest is the yttrium phase, yttrium elliptate. And it turns out to be a textbook spin glass. Here's, you've seen this before, the DC susceptibility, the AC susceptibility, the linear heat capacity, and something called the non-linear susceptibility. We were doing this work, as you see, a while ago. Eugene at the University of Waterloo, and Bertram was all the Boston University were involved in this work. So this is completely unexpected. There's no a priori reason why this should be the case. And so we wanted to look at this. We wanted to look at this in some detail. The conventional wisdom with respect to the spin glass state is the following. You need two criteria. You need frustration. Well, that's no problem. That's built into the pyrochlore lattice. But you also need something, some kind of positional disorder, some randomness somewhere. So we look for disorder in the average structure of the diffraction patterns. And these were data originally taken by Jan Reimers and analyzed. We analyzed every possible substitutional disorder, displacement of atoms here and there, and none of them worked better than the average structure. We did the same when we had, when data, slightly higher resolution data became available at the Lujan Center. We did the same thing, and the average structures refined perfectly to well-ordered perovskites. So, of course, we wanted to take a look at the local structure. And I won't go through the details here. I just want to recognize We worked with Thomas Profin. Thomas designed and built the NPDF instrument at Los Alamos. It is now sitting there unused as the Lamont Center shut down. As far as I know, I was talking to somebody from Los Alamos a couple of months ago. It's not been cannibalized, but it's not being used. At the time, it was the world's best instrument for neutron PDF, and it probably, I think, even today still, it would be. It's that good. But it's sitting there. Okay. All right, so my next comment is that I will quote Mr. Vera again, by paraphrasing. You can see a lot just by looking at the diagram. So this is the geobar, raw geobar, and I focus your attention on the yttrium oxygen 1 peak. It's got 6 neighbors, and so its intensity in the geobar should be almost the same as the intensity in the aluminum oxygen peak, which also has 6 neighbors. By the way, the scattering rates of yttrium, oxygen, and aluminum are all pretty much the same. That's another feature of neutrons. So it's clearly sign of disorder. It's very weird. It shows up very simply in this peak. But by the way, we were working. This is the very early days of NPDF. We were working with Simon Village's group. Simon was still at Michigan State. That's how long ago this was. And the postdoc actually who did the work was Diego Zano. At this stage of development of the analysis tools for NPDF, or total scattering, the large box RMC methods were just under development. So we were using small box approaches, and of course we tried to model the geobar with the fully ordered static model, and that fails miserably, of course. We knew it would. So our best approach was to try a split site model. There's a 96-fold site. The oxygen is normally in oxygen ones are normally in a 48-fold site, so we split them into a 96-fold site. We had some extra parameters to work with, and of course we got a better result. But again, we at this stage we weren't able to apply the full power of the RMC methods. Okay, so since we published our original work in the late 80s and early 90s, the papers have been cited an amazing 1,200 times. So a lot of people have been interested. And there's three other approaches to working out what the disorder model is for this material. And probably the final word is here, 2017, some 30 years after the initial report of the spin-glass behavior. It's a very complex orbital dimer model of Joe Pattison using the RMC approach. And that seems to be the last word. It took 30 years to figure it out. Okay, so I just want to finish by making comments about some other features of the pyrochlore oxides, which are remarkable. I just go back to this local symmetry of the rarest site. It's extremely strong axial symmetry. When you work out the crystal field expansion, the crystal field potential, the axial term, the first term, so-called B20 term, is extremely large due to this strong axial symmetry. And an implication of that is that the rare earth moments are strongly pinned along the directions of the 1-1-1 axes of the tetrahedron. And so, for example, here's a couple of the cases. These can be perfectly understood by examining the sign, as it turns out, of the axial term in crystal field expansion. For dysprosium and holmium, we have the 2-in, 2-out model. The moments are parallel to the tetrahedral axes, and for erbium and most are normal for the tetragrammaton. So this is totally understandable in terms of the crystal fields in there. One very famous implication of this is the following. You probably know about this. It's so-called spin ice state. Low temperatures, dysprosium and holmium titanate fall into this spin ice state. It's called a spin ice state because it maps exactly onto water ice. Right? Here's water ice. Each oxygen atom in water ice has 2 covalent bonds and 2 hydrogen bonds, 2 in. And that's exactly the same statistical situation as the 2 in 2 out model for holmium and dysprosium. And when specific heat is measured, you find that not all the entropy that you expect is there. Both dysprosium and holmium, the ground state's a doublet, so you should be getting an entropy loss equal to R ln 2. In fact, the actual entropy loss is R ln 2 minus 1/2 ln 3/2, and this is exactly the result that Pauling got many years ago for water ice. Okay, so I just want to mention a couple of other collaborators before the last slide. Bruce Golan, a colleague in McMaster, has been with us from the very beginning. He's an expert in neutron scattering. And he's still studying pyrochlores, although I don't do it anymore. They published a very nice paper on cerium zirconium oxide, and they're claiming evidence for all of the buzzword topics these days. It's a spin liquid. For particular varieties, all kinds of spin liquids now, just roughly one for theorists. It also shows dipolar and octopolar magnetic ordering. So you can get anything, you can get all kinds of stuff. Perovskite zirconium. And Jason Gardner. Jason was my collaborator on the review paper. Jason, I didn't recognize him. He now works at Oak Ridge. I didn't recognize him. Never seen him in a coat and tie before. The thing best I remember about Jason, evening spent at the Long Shots Sports Bar in Deep River, Ontario. And that's where the Chalk River facility was located on Hot Wings night. He wasn't wearing a coat and tie. So I'm just going to comment that pyrochlore oxides remain a topic of intense interest. A couple of weeks ago, I plugged magnetic pyrochlore oxides into Google Scholar and I got 17,000 hits. It seems like a large, that seems too large for me. But anyway, that's what we got. And I don't do this myself anymore. I don't apply for funding. But I understand these days when you apply for funding, you are supposed to tell them how many jobs you're going to create with the results of your research. And so, well, somebody is paying these guys to do the research and write these papers. So I think that's sufficient justification for this kind of work. Okay, so anyway, I want to thank you for your attention. And, I got some other ducks here. That's a fin-tail duck and that's a mandarin duck. Okay, so thank you. I think almost finished on time.
Thank you, John, for the wonderful talk. Are there we have time for a question or two from the audience?
What is the origin of the metal to insulator transition?
Yeah, that's a subject of considerable controversy. I wrote about this in the review article. It's not a simple model to explain. I don't have any slides. I probably should have brought some. It's very it's hard to understand because the bond angles don't change, and it's just a matter of changes in. It's not a simple model. I'm not sure if that's the consensus our own understanding.
Are there any other questions for John?
Oh, Brandon.
This might be a bit off the wall, but how are we doing in our ability to predict magnetic properties?
Pardon?
How are we doing with the ability to predict magnetic properties from simulations? You do experiments.
Yeah, I'm probably not the right person to ask about that. I'm not I know we have a lot of collaborators who do a lot of DFT calculations. I don't think, I think you can probably rationalize structures with DFT after you know what they are. I don't know about predicting.
It's my impression that they're not catching that in complicated systems like this, but I don't know.
Yeah, that's probably true. Yeah.
Thank you, Brandon. Any more questions? If there are none, please join me in thanking